Today we're talking about Newton's three laws of motion. Many students think they understand Newton's three laws because they can quote them. And you do have to know what they are. But we are not interested here in you being able to learn something off and regurgitate it. You have to know what they are so that you can apply them to situations. And of course, everything around us that moves because of Newton's three laws. So, how does a bird fly? How do airplanes work? How do you even walk? Newton's three laws help to explain all of that. In order for us to be able to do anything, we have to be able to exert a force on an object. We will come to what those forces do, but fundamentally we need forces. And that object helps us out. When we push it, it helps us out by pushing us back. That is the fundamental origin of forces. So if you think about walking, you look at the man walking along in this picture here, in order to propel himself forward, he has to push the ground backwards. What the ground then does, of course, is in turn pushes you forward. So forces always come in pairs. This is the fundamental thing. If you want to have a force to propel you forwards, you have to first exert a force backwards. And so we are going to start with Newton's third law, perhaps an unusual place to start. But this is the law that says that forces occur in pairs. And if you're going to quote the law, quote it properly, it says when object A exerts a force on object B exerts an equal and opposite force on object A. A lot of the time you hear it quoted as for every action there is an equal and opposite reaction, but the real way of saying it is this. And of course, when we have pairs of forces like this, we call them action and reaction pairs. So your action is to push the ground backwards, and the reaction from the ground is to push you forwards. Nothing, and I cannot emphasize this enough, nothing happens without this first step. If we look at the example of the bird, what the bird has to do is the bird has to push down on the air. And as a result of the bird pushing down on the air pushes the bird up. Once the air starts pushing the bird up, we can start looking at the forces on the bird. We will get to that in a moment. So this is where it begins. The bird has to push the air first downwards so that the air pushes the bird up. Another example that you see is this. So the skin of the balloon, the outside of the balloon, pushes the air out the back of the balloon. And as a result of the balloon pushing the air pushes the balloon back. And so the air being expelled out the back pushes the balloon forwards. This is the essential principle of a jet engine. So this is how aeroplanes accelerate forwards, in that the engine pushes the air out the back, the gases out the back, and the gases push the engine forwards. The engines happen to be attached to the plane, and so the plane experiences a force forwards. Another example that is fairly intuitive for people to understand is the act of swimming. You have to grab the water and push the water backwards. And as a result, the water pushes you forwards. And so if you've ever done any swimming, you know that you have to grab that water and pull it back so that you can propel yourself forward. Now we're going to be looking at this particular swimmer and this system in more detail. So here we see our fundamental Newton's third law pair here. In order to propel herself forwards, the woman has to exert a force on the wall. So first of all, she's responsible for pushing on the wall. The wall then pushes her back. So this is where everything begins, and we will look at what happens next in a moment. There are certain fundamental rules or properties of third law pairs. So they are always equal in size. So the magnitude of the force that the wall pushes on the girl is exactly the same magnitude as the girl pushes on the wall. They are always opposite in direction. So they're along a line, in a plane, in the opposite direction to each other. They have to be the same type. So you could take the example of the Earth and the Moon. The Earth exerts a gravitational force on the Moon. The Moon exerts a gravitational force that is equal in size, but opposite in direction on the Earth. and they have to act on different objects. So this is the one that gets people a lot of the time. They think they understand Newton's third law, but you have to remember that we're talking about a pair of objects here. Girl pushes wall, wall pushes girl. They act on the other object. We're not talking about all the forces acting on an object here. Again, this is going back to where forces come from originally, and they come from one object pushing another and therefore getting a pushback. This was our first specification point. We needed to know and understand Newton's third law of motion. So know means you do have to know what it is. If object A exerts a force on object B exerts an equal and opposite force on object A. But also understand. So the fundamental part of this is the understanding. You need to be able to look at a force and say what its third law pair is. And if you follow the rules, you'll be able to identify those very easily. Because we need to know the properties of pairs of forces. That's those 4 rules. So let's go back to our girl on the wall. We know this is our Newton's third law pair here, our action-reaction pair. What we now need to do is look at what happens to the girl. Because this is going to bring us to our next law. In order to figure out what happens to the girl, we have to look at all the forces on the girl. So we know we've got the force of the wall on her feet, and that is going to push her in that direction. We also know that we're going to have some drag from the water in this direction. It's not so easy to move through. If the push on the wall from the wall on her feet is less than the drag, nothing is going to happen. But the idea, of course, in pushing yourself off a wall here is to make the force from the wall on your feet greater than any opposing forces. And if it's greater, we will have a resultant force, and that is the key to everything. Because Newton's first law says an object will continue in a straight line at a constant speed. In other words, at a constant velocity, unless you get a resultant force. So without one force being bigger than another, the object will just continue on the way it was. Now that could be stationary. A velocity of 0 is still a constant velocity. That could be at a constant speed. So if it's already moving 5 meters per second, it will continue to move at 5 meters per second. That could mean that the object, if it does have a resultant force, is going to change its direction. Its speed might not change, but its direction might. So there are lots of conditions that if you pick apart Newton's first law, you start to see it is a much deeper thing than it looks at first. And here are the consequences of this. Any change in velocity, either a change in the magnitude of the velocity, also known as speed, or a change in direction is called an acceleration. So it doesn't matter whether your direction changes or your speed changes, or both. Any change in velocity is an acceleration, and in order to have an acceleration, you must have a resultant force. If you don't have a resultant force, which is strictly what Newton's first law is about, no resultant forces, no acceleration, no change. If you do have a resultant force, you are always going to have an acceleration. There are no exceptions to this. So if you can identify that there is in fact a resultant force, you are going to have a change in the motion of the object in the direction of that force. The flip side of that is if you witness an object accelerating, so either speeding up, slowing down, or changing its direction, then you know that there must be a resultant force. There's no two ways around it. If it's accelerating, it's got to have a resultant force. And that resultant force will be in the direction that it's accelerating. If there's no change, no resultant force. Again, no exceptions. So if you look at an object and there's no change in its speed or its direction, then you know that any forces that are on it, either vertically or horizontally, must be balanced. Again, no exceptions to this. And then, flip side of that, if those forces are balanced, so you know the forces are balanced, then there cannot be a change in velocity. Its speed cannot change, and its direction cannot change. So it's a very, very cut and dried law, this. If you have a resultant force, you get an acceleration. If you don't, you do not. What about if you do have an acceleration? This is what Newton's second law does for us. If you do have an acceleration, you do have a resultant force, how much acceleration do you get? And this is written in our specification as the sum of F. In other words, the resultant force of F is equal to ma. And that's quite important, because a lot of people forget that the F in F equals ma is the resultant force. Not just the force acting on the object, but the unbalanced force that's acting on the object, because that's the one that's causing the acceleration. So our second specification point was to be able to use the equation sum of F is equal to ma, or resultant force is equal to mass times acceleration, and use this equation in situations where m is constant. And it says including Newton's first law where there is no acceleration. So we have already covered that. Now, it does add in italics use of the term terminal velocity is expected. And we would use this when we reach a point of zero acceleration, because the forces on an object will change. And so we say that an object has reached terminal velocity when its velocity becomes constant, because the forces have become equal when they're in opposite directions on an object. We're now going to talk about drawing free body force diagrams. And in order to draw a free body force diagram, you have to be able to identify the center of gravity of an object. And for regularly shaped objects, that's fairly easy. You're finding the center point, so you would put, like I've drawn here, the two green lines going from corner to corner. The center of gravity is where those two lines cross. For any circle, the center of gravity is at the center. Even if it's a donut shape, for example, like this, your center of gravity is still going to be in the center of the regular shape, even if that's in the hole of the donut. And for a triangle, you bisect the angles and you find the center. For irregularly shaped objects, it's a little more tricky. You have to use a plumb line. This isn't in our specification, finding the center of gravity of an irregularly shaped object. But essentially, you hang a plumb line from a hole in the object at 3 different points. You see where the plumb lines cross, and that will be your center of gravity. What we're interested in about the center of gravity is that this is the point from which the weight of an object, the gravitational force, appears to act. So when we draw free body force diagrams, we always draw them so that the lines come from the center of gravity of the object. It's tempting to draw, this is normal contact force, it's tempting to draw normal contact force from the surface that the object is sitting on, because of course that's what the normal contact force is. But you should be drawing it from the center of gravity of the object. And so when a box is sitting on a surface like this, weight is acting downwards, that's gravitational force. The force that is balancing that is the normal contact force. It is worth remarking here that these are not a Newton's third law pair. First of all, because they're acting on the same object, the box. They're not the same kind of force. One is gravitational force and one is electrostatic force, a normal contact force. So be very careful. This is a Newton's first law pair, if you like. These are the forces that are acting on the object, and we have to assess, are they the same size? And if so, the forces are balanced, and if not, the forces are unbalanced and will cause an acceleration. One of the interesting things you have to be able to do with free body force diagrams is talk about what happens when you put an object on a slope. Here we have the same box on a 30-degree slope, and so we're going to start drawing in our forces. Weight always acts downwards from the center of gravity of the box. The normal contact force acts from the center of gravity of the box, perpendicular to the surface. Now our normal contact force is acting in this direction. And you can see the normal contact force, even if the arrows were the same length, is no longer along the same line as the weight, and so it's not balancing the weight. And obviously, as we know, this box is going to slide down the slope. But what is the force causing it to slide down the slope? In order to answer that question, we need to look at what force is parallel to the slope. Now, obviously, we know it's something to do with the weight of the box. We should also know that it is going to slide down the slope slower than it would free fall. So it's something to do with the weight, but it's not the entire weight, because the entire weight would make it free fall. So if we think about the forces, we know that we can make a triangle. This angle will also be 30 degrees. For various reasons, mathematical proofs, or if you just really think about what would happen if this slope were flat, and what happens as you increase the slope, you'll see it should be 30 degrees. This side is the opposite side to that angle. This side is obviously the adjacent side. The force that is sliding the box down the slope is the component of the weight that is parallel to the slope, that one there. And we know that the sine of 30 will be equal to opposite over the hypotenuse of that triangle we've drawn. Therefore, the sine of 30 will be equal to the component of the weight parallel to the slope over the weight, which means that the component of the weight parallel to the slope is going to be W sine 30, or sine theta, if you want to be more general about it. So when any object is sliding down a slope, provided you know this horizontal angle that the slope is making, the parallel component, the component that is causing the box to slide down the slope, will always be W sine theta. The adjacent side is now balancing the normal contact force, so that's going to be equal to the size of the normal contact force, this blue force up here. The specification point that went with that was be able to draw and interpret free body force diagrams to represent forces in a particle or an extended body using the center of gravity. Let's look at some tricky situations that might involve Newton's first and second laws. So this is a man in a lift. The lift is going at a constant speed. What can we say about the forces on the man? Well, we know that the weight of the man is acting from his center of gravity downwards. Because the lift is going at a constant speed, and therefore the man is going at a constant speed, we know that the normal contact force from the floor must be equal to that weight, and it's pointing upwards. What about when the man and the lift are accelerating downwards? Well, if they're accelerating, we know that we must have a resultant force downwards. And that means when we look at the weight of the man versus the normal contact force from the floor, the weight must be greater than the normal contact force because we must have a resultant force downwards in order for the lift to accelerate downwards. Applying the same idea to the lift accelerating upwards, we know that our resultant force has got to be upwards because our acceleration is upwards. Again, if we draw in the weight of the man and the normal contact force, this time the normal contact force must be greater than the weight. What the man feels inside the lift is the floor pushing him upwards, because that normal contact force comes from the floor. Because the floor pushes him upwards, he's going to feel slightly heavier inside this lift. What about the situation of decelerating upwards? If he's decelerating upwards, it means he's slowing down, traveling on the way up, but slowing down. That means that the resultant force must be downwards. So if we draw in the free body force diagram, there's his weight. The weight has got to be greater than the normal contact force so that you have a resultant force downwards, and that is going to be pulling on the lift, slowing it down. And our last situation, decelerating downwards. So the lift is traveling downwards, but it's slowing down. So that means that your resultant force has got to be upwards. And so we're back again with the weight of the man and a greater normal contact force so that we can have a resultant force upwards. And again, the man will feel pressed into the floor here. Now these are classic examples of lift and man. This idea of where you might feel pressed into a chair or pressed into the floor comes into a lot of situations. And what you have to remember is you feel pressed against that surface when that surface is pressing against you, because it is pushing on you. And if you're slowing down in that situation, it means that surface is slowing you down. So these 4 examples are carefully chosen to give you an idea of how you should think about these situations. That's it for Newton's 3 laws. Let's have a brief recap. The third law tells us about pairs of forces. It tells us where forces come from. If you want a force to propel you forwards, you have got to exert a force backwards on the object that's going to propel you. Newton's first law tells you what happens when there is no resultant force, or when there is no acceleration. Those 2 things are bound together. If you have acceleration, you have resultant force. If you have resultant force, you have acceleration. Newton's second law tells us how much acceleration for a given mass is caused by a particular resultant force. Remembering that F in that equation is the resultant force. And free body force diagrams are always drawn from the center of gravity of the object. You put your arrows from there. You try to keep your arrows proportional to the size of the force. So if the forces are equal, your arrows are approximately equal.